Here we're going to take a look at the cardiac cycle. This is really the events of a single contraction of the heart. The image you're looking at here takes you through the steps in the EKG, which you've already been through in lecture, and shows you how the movement of blood and the contraction of the heart versus the atria and the ventricles match up with the EKG. But I'm going to take you through this step by step. So the next slide here takes you through, each slide is going to take you through the different steps of the cardiac cycle. But before I walk through these and the information that's on here, I'm going to jump to the very next image. Actually, not this one, but this one here. This picture here is from your textbook, and it shows you these phases as well without the EKG brought into it. So when we say the phases of the cardiac cycle, we're going to start with the contraction of the atria. We're going to move through then to the contractions of the ventricles and movement of blood through. That's what these purple ones are through, and then that relaxation period, and then back through the atria again. So this image also kind of helps you with that flow of blood, and also shows you the steps with regards to what's happening with the valves. So when we work through cardiac cycle, you want to be thinking, where's the blood at? What are the valves doing? And what part of the heart is actually contracting? So if we go back up then to the beginning of our steps here with the cardiac cycle, we always begin with the atria or atrial systole or systole. And I think I gave you those terms in class already. Systole means contraction. Now, it lasts about 1/10 of a second. At the time that the atria are contracting, the ventricles are relaxing. So it's important to understand, if we drop back up to this picture here, at the point at which the atria begin to contract, we're coming in on the P wave, the AV valves are open and the ventricles are relaxed. So as we move through that actual contraction, and blood will move in to, and this is not showing blood, this is showing the electrical current. That's what the green is showing, is the electrical current. The blood will be pushed through the opened AV valves, and the ventricles will complete their filling of blood. Just prior to this point, the valves have been laying open and blood has been pouring in from both the right and the left side. Now, I'm going to give you some numbers here. I don't need you to have any of the numbers memorized, so don't worry about that at all. If I need numbers, I'll give them to you, but you do have to understand some terminology and concept. So, at the point at which the atria contract, the blood is forced through the AV valves into the ventricles. That's what's happening during that contraction. So blood has already been passively filling into the ventricles, but now we squeeze out the remaining blood with the atria contracting. At that point, the atria will finish their contraction. They will enter into relaxation. But about 105 milliliters of blood will flow into the ventricles prior to the contraction. Then during the contraction, another 25 or so will be squeezed in, so for approximately 130. Now again, it's not that I need you to know these numbers, but what we call that volume that enters into the ventricles after atria is contracted, how much is in there, we refer to that as end diastolic volume. Remember what it says in the beginning, while the atria is contracting, the ventricles are in diastole or relaxation. So at the point at which they are just about to begin to contract, they've received all the blood they're going to get, we refer to that as end diastolic volume, or EDV, the amount of blood that is in the ventricles at the end of their relaxation. So again, the actual amount will vary. This is an average that's given here, but that concept that at the end of the relaxation of the ventricles, they're getting ready to contract now, that's how much blood is in there. That's the total volume that's in there. We'll then move into ventricular systole, and the atria are now in relaxation. Notice this one lasts about 3 times longer. Pressure rises in the ventricles and pushes close the AV valves. I've already mentioned that's how the AV valves close. There is a point in time, and I'm going to jump back up to our picture here, and there is a point in time where all the valves are closed. So where the ventricles are just about ready to contract at this point, and if you can kind of see in our picture here, and if I jump to the very end where the one other picture I said for you to look at, there's a point at which all 4 valves are closed. So if you look on the picture here at these valves, we have what's called isovolumetric contraction. The atria contracted, the blood flowed in, the ventricles are now getting ready to contract. The muscle fibers are just about to shorten, Again, we're taking what takes less than about a second to occur, and we're stretching this way out. So it's important to understand that. So at isovolumetric contraction, all the valves are closed, and there's pressure that's building up. So the blood has closed the AV valves, and the semilunar valves are not open. That period of time is referred to as isovolumetric contraction, a point in which no volume of the heart changes at all. Nothing's moving in or out. So it's just about 1/10 of a second's worth of time in this whole process of ventricular systole. Then, as the pressure starts to rise in there, as the fibers shorten, that reduces the volume inside the ventricles, and the pressure has to exceed that which is in the aorta on the left side and in the pulmonary trunk, which is in the right side. And I gave you some values here. Again, don't really need to know these numbers specifically, but understanding that the aortic pressure has to be above, it's usually at about 80, so we've got to exceed that pressure to push those valves open, and in the pulmonary trunk about 20. At that point, when the pressure is great enough to push open those valves, remember, when we look at these valves, actually let's go to this picture here for a second. When we look at these valves and we have to open this one and we have to open that valve, coming up the aorta here, remember there's blood in there. The weight, the volume of the blood that exists in the aorta, it's never empty, or the pulmonary trunk, it's never empty. That has to have a volume in there. That means we have to push that blood out of the way in order to open up. And so therefore, we have to exceed that pressure. And we refer to that as ventricular ejection, or that movement of blood out of the ventricles into either the aorta or the pulmonary trunk. So ventricular ejection is that movement of blood out of the aorta, or out of the ventricles and into the aorta or into the pulmonary trunk. On average, the ventricles each equally should eject the same amount of blood. The blood volume moving from right side to left side and from left side out to the body should be the same with each contraction. And if it doesn't, we've got a problem with the heart. The heart is failing to work correctly. But what we have is a normal ejection of about 70 milliliters. Again, a value I'm not asking you to memorize, but the concept is that the stroke volume is the amount of blood ejected with each heartbeat. We're measuring what's coming out of the ventricles. That's what's going either to the lungs or going to the body tissues. So the stroke volume is the amount of blood ejected with each beat, or each contraction of the ventricles. So, like I said, approximately 70 milliliters gets out with each normal average heartbeat. So, or contraction of the ventricles. So, in ventricular systole, we expect about 70 milliliters to get out. Now, that means we didn't get it all out. So, at the end of ventricular contraction or systole, as the pressure drops back down and blood starts to flow back and get caught in those cups of the semilunar valves, and we talked about how those valves close. We push the blood out, and then blood starts to backflow as the pressure drops, gets caught in the cusps of those valves, and closes the aortic and the pulmonary valve. That means there's some blood that's left inside the ventricles. That's referred to as end systolic volume. Recall what we had said earlier. Let me go back up and say the ventricles each had about 130 milliliters in our example here. Okay? If we say we had 130, and at the end of ventricular ejection, we have sent out about 70, we will have about 60 left. That there was 130 total. So here's our first real calculation. Stroke volume, SV, is equal to the end diastolic volume, EDV, how much was in there right before the ventricles began to contract, minus ESV, the amount of blood left in the ventricles after they have contracted. That'll give you stroke volume. So SV is equal to EDV minus ESV. That's the formula. The amount of blood we eject is equal to the amount that was in there to begin with minus the amount that's in there when it's over. So that's what end systolic volume is. How much is left after the contraction has occurred and the valves have closed up again. Okay? Another term you need to know and another calculation you need to be able to do is the ejection fraction. That's the percentage of blood that's ejected. So it's using the same numbers, but it's just, instead of giving us a volume, it gives us a percentage. And for that one, you take the stroke volume, how much this was, and divide it by whatever EDV was, times 100. We'll do one of these calculations in just a minute. Okay? Now, let's jump to our picture here for a second. We've now had atrial contraction. We had that isovolumetric contraction. All the valves were closed. And then we ejected the blood, about 70 milliliters. And now we move into a relaxation period. And in this relaxation period for the ventricles, we first have what's referred to as isovolumetric relaxation. And for a period of time, the atria and the ventricles are both relaxed. Notice on our picture again here, if I keep jumping back and forth, there's a period at which the AV valves were closed and the semilunar valves have closed because the blood backflowed down into the aorta as the pressure dropped and got caught in those cusps and closed those valves. And for a brief moment in time, again, all 4 valves are closed here. Isovolumetric relaxation. Very quickly thereafter, the AV valves will open up because pressure is going to drop, the muscles relax, the papillary muscles and cords relax, and blood begins to flow passively back in from the atria into the ventricles. So this blue box here is entirely relaxation time. The ventricles are not contracting, nor are the atria contracting. So that's what, jumping in the wrong way. So in this relaxation period, both the atria and the ventricles are relaxed. Skip my second bullet point here. This brief period of isovolumetric relaxation occurs, and then as the ventricular pressure declines, muscles relax, AV valves open, and we begin to fill again, getting ready for the next heartbeat. Note my bold statement here. A faster heart rate will shorten this relaxation period, but have little effect on both the atrial or ventricular systole. So the contractions really can't speed up. What speeds up primarily is the relaxation period. If you start to take away from the contractions themselves, then you have a problem with function. So under a normal function, if we increase our heart rate while we exercise or are in a sympathetic response, we'll reduce relaxation period, but we will not reduce the actual contraction times. Those do not change under normal functions. Even though a higher heart rate is still normal, it's extremely high that we move into the abnormal state. All right, here's some of these calculations and a couple of other terms I need you to know. Let's first do a little math here. If EDV is 150 or 150 milliliters and ESV is 50 milliliters, what is the stroke volume? If you remember your formula, stroke volume is equal to the EDV minus the ESV. Then you have 150 minus 50, so your stroke volume is 100 milliliters. Just as simple as that. How about the ejection fraction for that same thing? If you just figured out that your stroke volume is 100, take 100 divided by the EDV, which we gave you as 150, and 100 divided by 150 is 66.666. So 66.67%. Remember, you take those two and multiply by 100, and you'll get your ejection fraction. In other words, on an average heart rate, about 67% of the blood that was available will actually be ejected out. So remember what we started with. We had 130 in there. We sent out about 70. 60 was left. So 70 is about 67% of the total volume of blood that was available, which was 130. So if you're struggling with that, go back and listen to it again. Slow me down and kind of work your way through it. The book also takes you through calculating stroke volume and ejection fraction. We have a couple of other terms here, 4 of them I need you to go through. One of them is another calculation that you are responsible for, and that's cardiac output. Cardiac output is simply the amount of blood ejected per heartbeat. Okay? I'm sorry, I take that back. The cardiac output is the amount of blood ejected per minute, and it's based on stroke volume times heart rate. I'm sorry about that. Didn't mean to confuse you. The stroke volume is the amount of blood ejected per heartbeat. Cardiac output is the amount of blood ejected per minute, because heart rate is a measure of the number of times the heart beats per minute. So, cardiac output is equal to the stroke volume, how much blood is coming out in one beat, times the number of times the heart beats per minute. So you simply take that value and multiply them together. So for instance, in our example just above there, our stroke volume was 100 milliliters were ejected with each beat. If you have a heartbeat or a heart rate of 70 beats per minute, you take 70 times the 100, and you have 7,000 milliliters per minute. And that's how much. So that's about 7 liters of blood per minute is pumped through your heart. If you start to think about that, that's an enormous volume of blood. So again, find your stroke volume. Heart rate will be a value that will always be given to you. Now, I might give you, for instance, on a problem, I might give you the EDV, and I might give you the ESV, and I'll give you heart rate, and I'll tell you to calculate cardiac output. So first you got to calculate stroke volume, and then take that stroke volume times the heart rate. So, and again, in our example, 100 was the stroke volume, and I gave you a heart rate of 70. 70 times 100, 7,000, and you have that, and it's always in milliliters per minute. Okay, so that's cardiac output, the amount of blood ejected per minute. 3 concepts that are very important that tie into that relationship of cardiac output and factors that affect how much output there will be. It's first the concept of preload. It's also referred to as the Frank-Starling law of the heart. And it's very straightforward. The greater the degree of stretch to a point, and I'll explain that to a point in just a minute, but the greater the degree of stretch, the greater the force of the contraction. It's kind of like taking a rubber band. The more I pull back on the rubber band, the further it flies. Now, the reason I put to a point in there is if I take my rubber band and I pull it to the max every single time, over time, eventually the rubber band will tear and break. Now, granted, your cardiac muscle tissue is not a rubber band, but if you are always asking the maximum, stretching the ventricles with the amount of blood that's come in, if you're constantly stretching them, you're asking so much of your heart, eventually the heart can start to wear out. We're talking over multiple years. In fact, we're talking 30 to 50 years as opposed to, 20 times for a rubber band practically. So that's important to understand. But preload's really linked very directly to the venous return or the end diastolic volume. How much blood is in the ventricle to begin with? The more you fill it with, the greater it stretches. The greater it stretches, the greater the force of contraction. Don't put a lot of blood in the ventricles. You don't have a lot of blood coming back. You will have less of a degree of stretch, and therefore preload goes down and cardiac output is going to go down. So I want you to be thinking about preload as a positive thing, a good thing. The things that can increase preload will increase cardiac output, and that's a good thing. You'll provide more blood for the body. Things like your sympathetic innervation of the heart, epinephrine, norepinephrine, those things will increase your preload because they'll increase the degree of stretch. Okay, so that can help. In addition to preload, I'm going to jump down here to contractility because it's very much linked to preload. Anything that increases contractility, epinephrine, norepinephrine, even calcium, which is necessary for the contraction. Think back to your cardiac cycle or your cardiac action potential. You need the calcium for the contraction to occur. So if there's more calcium to a degree, you will have a greater force of contraction, and therefore you'll have a greater preload. So contractility is how well do those fibers contract. So we're looking at anything that can increase the blood coming back to the heart and increase the contraction will actually increase preload. Now, afterload is a different concept altogether. So preload, contractility linked together. The greater the strength of the contraction, the greater the forcefulness, the greater the preload. But afterload refers to the pressure, and this is key, and I ask about this on every exam, It's the pressure that must be exceeded before we can eject blood from the ventricles. So remember before we talked about the ejection and we had to exceed 80 in the aorta and 20 in the pulmonary trunk. Well, these two values really represent the afterload. How much pressure is there, how much volume of blood is there in those two vessels, and primarily we're always looking at the left side of the heart, so we're really looking at the aorta. What do we need to do to push that blood out of the way and get the blood out to the body tissues? That's the afterload. What pressure must we exceed? So if the pressure in the aorta is at 80, that's not so bad. That's a manageable pressure. But if this jumps up to 90, 100, 110, the afterload increases. The heart has to work harder to eject the blood. So afterload, and any kind of increase in afterload, is a negative thing. It makes it harder for the heart to function. So afterload's the pressure that must be exceeded before ejection of blood from the ventricles can occur. Think of it as a negative thing. Something we want to try and reduce afterload. So afterload is very much linked to what the body's blood pressure is. How much volume of blood is out there in the system, and do we have to work harder to pump that volume of blood? All right, these pictures, as I've been kind of jumping back and forth on your book, I believe it's all one big picture. Some of this stuff's a little hard to make sense out of it all, but this bottom piece here is the most important part of this particular image because it reminds you of what the steps are in the cardiac cycle and gives you those isovolumetric contraction relaxation images.